All right, so problem number 1, let f be the function f of x and g be the function g of x. At what value of x do the graphs of f and g have parallel tangent lines? So parallel tangent lines tells us that the slope of the tangent lines should be equal, because remember, parallel lines, slopes are the same. So really we need the derivative of these two functions to be equal to each other. So what we're going to do in our calculator is go and type in each of these. And then we're going to go find the derivative of each. So remember, we hit Math 8 to do the derivative, and if you've got a fancy calculator, yours looks a little bit different, and you'll do alpha trace to pull our y1. I am going to pull that in the vars functions, and we want x equal to x because this means we're finding the derivative everywhere as opposed to just at one spot. And then when we go to graph this, because we want to find where the derivatives are equal, we actually don't care about the functions themselves. So I'm going to go turn those off by hovering over the equal sign and clicking enter. So now we're only going to graph our derivatives, but we want this to graph quickly. So I'm going to go down to our window, go to XRes, make it like 3 or 5 or something bigger than 1 just so it graphs quickly. And it didn't give us a window here, so we can just leave our window like that. Let's click graph. Uh-oh, I typed y1 in here. Okay, let's click graph. All right, so I can see that there's an intersection happening here, but it's really hard to tell. So I'm going to actually go into my window, change my x-min to -3 and x-max to +3, and my y-min can probably be 0 because it looked like it was all above the x-axis. All right, that gives us a much prettier picture. So again, our goal is to figure out when these two graphs, these are the derivatives, when these two graphs are the same. So we want this intersection point. So we're going to hit second trace, intersect, and then since we've only graphed the two derivatives, we can just hit enter for the first curve, enter for the second curve, enter to guess, and it gives us our intersection. It says x value, so we want -0.391, so our answer is going to be C. All right, problem number 2. Particle moves along the x-axis, so that at any time greater than 0, its velocity is given by this. What is the acceleration? So we're given velocity, we want the acceleration at a spot. So we need the derivative of the velocity. So I'm going to go into my y equals and type in this function, 3 plus 4.1 cosine of 0.9x. Oops. And it says t in here, but our calculator is just like x's. So now that's in my y1, and I actually am going to leave these here so I don't have to type them in again, but I'm going to turn them off. Because all we really need is the derivative of this function. So if I go back to my home screen, second quit, we can pull up the derivative, Math 8, of y1 at x equals 4. So in the fancy calculators, that'll look a little bit different. And here is our value, 1.633. So again, that's because we were given the velocity and we needed the acceleration. So we just needed to do the derivative of the velocity at that spot. All right, question number 3. Two particles start at the origin and move along the x-axis. We've got a window here. Their respective position functions are given by these two equations. For how many values do the particles have the same velocity? So if we have the positions, we want to know where their velocities equal. That's going to be where their derivatives are the same. So into y equals we go. I'm glad I left these two derivatives here because I'm going to go ahead and put our two functions into y1 and y2. and we need to go turn off y1 and y2, and then turn back on our derivatives. Because here we want same velocity, so we want the derivatives to equal each other. They gave us a window, so let's go and double check. Our window should be 0 to 10 for our x's. It doesn't say anything for y's. The fact that it's got sine in it tells us we can probably make this like -3 to 3 for our y's, and that should be sufficient. But let's see if that's good enough when we go and graph it. Okay. Ooh, interesting. So this first one is our sine wave, and the second function appears like it goes up here and stops, but it might actually keep going. And that would really change our answer, because remember it says how many values do they have the same velocity on this window. So if it keeps going, it's going to keep intersecting along here. So we can check this in a couple of ways. One thing we could do is just go look at the table. So if I hit second graph, my y4 is that derivative of the second function. So if I look here, the fact that there are numbers here means that it doesn't just stop, it's just really, really small. So that means it does go up here and then it just gets really, really small and kind of grazes along the x-axis. And that kind of makes sense if we think about this exponential function, that it has that horizontal asymptote there. Another thing we could do is go and find the intersections. So I can do second trace, intersect. I can clearly see one right here, but I want to check if there's one like here-ish. So I'm going to go put my cursor there, hit enter, enter, enter. And sure enough, there is an intersection here. And if we want to check over here, second trace, intersect, scroll over, enter, enter, enter. And there's another one here. So we've got 1, 2, 3 intersections. This is really, really tricky because it's hard to see that. Another way you could maybe get around this kind of issue of not seeing this is just zooming way in on your y scale. So we could make the y's -1 to 1, see if that helps. Not really. It's really tough to tell that that keeps going. And maybe if you have one of the newer calculators, you might see a little bit clearer, but on mine, that's really tricky. All right, we've got one more problem here. The position of an object attached to a spring is given by this equation. Time in seconds. In the first 4 seconds, that gives us a window. How many times is the velocity equal to 0? So we're given position. The velocity will be its derivative. So in my calculator we go. I'm going to type in this function. And we don't really need the function itself. We can turn that off. We do need its derivative. So I'm glad I still have my derivative here. There's nothing in y2, so this probably wouldn't graph anything, but I turned it off anyway. So they gave us a window, right? First 4 seconds. So we're going to go make our x min 0, x max 4. Because we've got a trig function, probably -3 to 3 is good for our y's. Let's go check. All right. How many times is the velocity equal to 0? 1, 2, 3, 4, 5, 6. So that's just how many times is it crossing the x-axis. So we've got 6, and that is our answer.